So, morning everyone. Welcome to Tuesday. So, so this week hopefully we're going to get a long way, hopefully finish these field effect transistors. Let me just check everything's okay. Yep. Looks good. Right. So, so last week we looked a little bit at the maths behind devices themselves, and showed a little bit about the sort of equations that might apply, and there was a couple of key equations because there's two main operating regions of a FET, a flat area and a more, well, linear area, a rising area should we say, and the FET allows us to use either or both of those areas in useful circuitry. So we're going to look at a few circuits now and get an understanding of how we can use these FETs in proper devices. So we're going to look at something called a common source amplifier, which is a bit like a common emitter amplifier if we were using bipolars, the same kind of idea, so same kind of results we should expect. And then we're going to look at something called a high impedance unity gain buffer, and the importance of why it's high impedance and the importance of it being unity gain will be discussed and explained, hopefully. And then we do something that we can't use bipolars for, analog signal switches. So these are just sort of switches, basically, for signals that are quite easy to use. And then we'll look at the MOS transistor rather than normal FETs, and extend our ideas to things called power MOSFETs. So these two bits here don't take very long at all, and these are the more interesting parts, I think. Right. So let's take this 2N3819 transistor, FET transistor that we've been looking at, the JFET. We've looked at it in modelling, and we want to use it as an amplifier. So if we want to get the maximum gain out of this, we know that the maximum IDSS, and therefore the maximum transconductance of this thing, occurs when we've got 0 voltage on this gate. So it's sort of biased at 0 volts at this point here. So VGS equals 0. Let's give our max. So let's just do that and see where that gets us, because that's a point we know about in this transistor, that if we have 0 volts across this gate here, we're going to get the maximum IDSS flowing through this device. And there are two ways of doing this. We can either just apply a small signal centered around 0 volts to the gate of this, or we can, if that's got a 0 offset, if this has got a DC offset on it, so it's not centered around 0, for example, if it's going from 0 to 1, so it's centered about a half, we can feed it into the system through a capacitor, because remember the capacitor blocks the DC, so we'd end up with a signal centered around 0, or centered with no DC coming through here. And what we would also then do is we need to make sure we've got a 0 voltage applied to this gate, so we attach a big resistor across it like this to 0. And this means, because no current is flowing into this thing here, that both of these must be at the same potential. This end is tied to 0, therefore this end must also be tied to 0. So we've sort of biased it at 0 with a huge great resistor here, and with no current flowing through it. So it's just pulled it to that point. This is called a pull down resistor. So now any signal coming through here will superimpose itself on top of this signal. Won't want to go down here because it's used a big resistor, and so we have a signal superimposed on 0. So we've effectively biased it that way. We'll talk a little bit more about biasing as we go forward, because this is quite a neat little trick, really. So if we consider small signals, so AC signals, we won't worry too much about the biasing at the moment, although I have just talked about it a little bit. We can use either of the other two circuits. We apply our small signal model, because remember we're looking at small signals, so a small signal of our circuit looks like the model of the transistor, which remember had this transconductance current source in the output, so the current source is controlled by this VGS voltage. So as we vary VGS, we will vary the current through here. And on the input side, remember there's an infinite input impedance to our FET, because that's what we've assumed it is, because it looks like a reverse bias diode. So this doesn't go anywhere, it just sits here. So VGS is the voltage that we're interested in across here. Let me just pull that pen up. So this is a little V. Looks like a big V, but it's a little V. VGS there, so any variation here manifests itself in a changing current going through here. That then flows through this resistor in this loop here, and then we'll get a voltage across this device here. And the voltage will be this way round because the current is flowing that way. Okay, and the size of the voltage will depend on the size of the current and the size of this resistance. Okay, so question is, what is the actual output voltage of this thing? So for that we need to get what GM is. Excuse me. Right, so in order to get maximum gain, we need a maximum value of GM. And we also want RD to be as large as possible, because the gain of this device we've just seen from the previous slide is going to be GM times RD. So effectively the size of the current, or something related to the size of the current, multiplied by a scaling factor which turns the current into a voltage, which is RD. So if we say that ID is 10 milliamps, because we've got a zero bias here, so this is ID equals IDSS, then we know we've got 10 volts here, and we know we would like to have 5 volts here so that it can go up and down equally, go up 5 and then down 5. It's got freedom to movement. So for VDS equals 5, we would have to calculate a value of RD of 500, because what we want is 5 volts across here, and we know we've got 10 milliamps flowing through it. So if we just apply Ohm's law to this, we get a value of RD of 500. Okay, and so from the equation for GM that we calculated, or we got earlier in the course, i.e. last week, we can then put in various values, and we get, well, we got the value of GM we calculated earlier for all these conditions of 10 milliamps. We've got 5.6 times 10 to minus 3, that's our value of GM. And then we've got 500, which is the value of RD, and that gives us 2.8. Okay, a gain of 2.8 is not great. Right, and so this is ostensibly the maximum, because this is the maximum value of GM that we can get for this, is when we have 10 milliamps flowing through here. But it turns out, paradoxically, we could actually get more gain by reducing the value of ID that's biasing this system, because if we reduce the current through here, we can make RD go bigger, because if there's less current, there's less volts dropped across it, and we want more volts dropped across it, so we have to make the resistance bigger, and then this scaling factor then goes up. But GM also goes down, so the question is, how much does this go down compared with how much this goes up? Is there a trade-off? So for example, if we reduced ID to 0.1 of a milliamp rather than 10, we can go back and calculate GM again, and GM comes out this time at 0.56, and this is the equation we would use. So this is K is the value for that particular transistor, and ID is the drain current, which is now 0.1 of a milliamp. Remember, it was 10 milliamps before. So we can calculate a new version of GM, which is 0.56. Now the new value of RD is, we want 5 volts across it. We've now got 0.1 of a milliamp going through it, so we calculate the new value of RD as 50k. And now the gain becomes GMRD, so 0.56 times 50 gives us 28. Okay, and the previous slide should have also had a minus sign as well, to be strictly speaking accurate. So it's my fault for missing that off. But so now 28 is bigger than 2.8, and all we've done is we've dropped the bias current down rather than having it at the biggest value we could have. So we've actually dropped the value of GM, but we've gained because RD has been allowed to get bigger within the constraints of the power supply we're operating with. So useful gain is possible. Gain reduces as the square root of GM, but goes up linearly with the resistance. See, this is a square root relationship, and the gain here is linear with RD. So we have to play around with ID then. So the fact that GM is a maximum for ID, for VGS equals 0, is not actually that helpful to us, although we thought it might be at the beginning. So we need to think of a way of biasing the device. So what we'd like to do is we'd like to make, for no signal coming in, okay, we'd like to have this value here, the voltage between these 2 points less than 0, negative. So the direct approach would be to have our signal coming in through an AC coupled source. So this is DC blocking, so this can be whatever it likes. We've got a big resistor here, and we attach the other end of this big resistor some negative value, and then because no current flows through this resistor, the other end must be at the same negative value, and we've ended up making a negative VGS. Okay, it's a very straightforward approach. It's not preferred because it needs us to be able to generate a negative voltage, and we're trying to operate this on a naught and positive supply, so we end up having to build a third supply that's negative. We can do it, but maybe there's a better way of doing it. And if we took this other approach, why does no current flow through the resistor? Because there's nowhere for the current to come from. Yeah, this, remember, is a reverse bias diode, this transistor here, so no current flows through here. That's the only way current can flow through this resistor is through here, because this is blocked because it's DC, so nothing can come through here DC wise. This is all DC because it's biasing. Okay, and the only other way current can get into here is through the device, and it can't get through the device because it's a reverse bias diode, so there's nothing going on in terms of current here if this is more negative. Well, no, because we're not dealing with the AC part of the signals. This is all to do with DC. This is just biasing. Alright, we're just considering biasing. Okay, so as long as we keep this point negative, no current flows through here, so this voltage tracks this voltage, and that gives us the amount of current that flows through this part of the circuit. Okay, so that's where we're going with this. This is a preferred way of doing it because we haven't got a negative supply. We've just attached the end of this big resistor to 0, which means that this ends at 0, but we've introduced this other resistor here with a little capacitor around it. We'll worry about that in a minute. So we've got another resistor here, and the question is, what difference does that make? And it's providing a little bit of feedback to us, and hopefully the next slide will explain that in a bit more detail. Okay, so it's going into a bit more detail what's going on here. So this is the bias region that we're interested in for VGS. So we can go from 0 all the way down to the cutoff voltage of minus of VT. So we want to be able to control our DC voltage to somewhere in here to set the overall gain of this system here. So we need to hold this below the source potential. And so although just pulling this down to a negative voltage looks attractive, it means we can't actually get any signal in now, because any signal coming into here will just go straight to this negative supply because it's connected straight to it, so there can be no variation of voltage here. So this is quite good if you want to make a constant current source. Just apply a fixed voltage here and you will get a value of ID according to whatever voltage you've applied here. So this can make a nice constant current source, but it can't make an amplifier because there's no way of getting a varying signal in, because this is always tied to a fixed negative voltage. Right, but if we add this source resistor in here now, if we attach the gate to ground, we see that VG is equal to 0. Here's 0, and it's attached to the gate, so that the voltage VG across here has to be 0, it's fixed. And if we go around this loop, then we can say that VGS, which is the bit we're interested in, that's the bit that controls the amount of current going through the transistor, not necessarily this bit here. It's just up until now they happen to be in the same value because there's been no resistor here. As soon as we put a resistor here, we've now got VGS, which is different from VG because there's a resistor in the way. So if we go around this loop here, we've got VGS and we've got VS and we've got VG, and therefore VGS is equal to VG minus VS. Whatever the voltage is here, with respect to 0, minus whatever the voltage is here, with respect to 0. That leaves us the VGS. Okay, VG we know is 0 because it's connected to 0, and VS is equal to ID RS. It's just Ohm's law across this resistor. Okay, and therefore that all boils down to minus ID RS, and that's a voltage, yeah, and it's negative. So VGS has been made to be negative by the addition of the resistor here and a little bit of Kirchhoff's law around here. So we can control the amount of negative VGS that we've got on here by the size of the resistance, and also by the value of ID. So that's really good. By just changing this resistor, and it's not quite straightforward as that, but we change that resistor, we can change VGS, and therefore we can change the bias current going through this device. But this is okay, except there's no way to introduce a useful signal, as the gate now is tied directly to ground. Yeah, there's no way of getting any other signal in here other than ground, because it's fixed to it. So we add this gate resistor, this big one here, and as already said, there's very little current, or ideally no current flowing through here, because this is a reverse biased diode junction, and it's what it looks like for a JFET. You know, for a MOSFET, it's just an open circuit because of the insulating gate. So if no current can flow this way because of the reverse bias diode here, then this voltage here must be the same as this voltage here. This one is tied to 0, therefore this voltage is tied to 0. So as long as very little current flows through here, you're absolutely fine. And that's why you make it a big, huge resistor. Yeah, you've got to physically tie it to that point, but you have to have a very, very big input impedance. Otherwise, as Samuel Stevens says, current could come through here and go through that resistor. And it's not going to do that because it's going to like to go into the device. You know, can't flow this way through the device, but it can go that way into the device. Right. So what happens? So as an example, even if you have a picoamp of reverse current, because there might be a little bit of current because the reverse bias diode still has these spontaneous hole pair combinations, electron hole combinations occurring, you get reverse bias currents, very, very small. So let's say it was even a picoamp. A 1 meg resistor with a picoamp flowing through it will only drop 1 microvolt across itself. So the only difference you've got here is this is 0 and this will be 1 microvolt. So we just call that still 0. You know, it's close enough to be not important. So we can still have a high input impedance, and we can capacitively couple a signal in. So now any signal coming in through here that's AC will go through this capacitor and it will add itself to whatever voltage it sees here, which is very close to 0, and that is the thing that applies itself to the gate. And if we change the voltage on the gate, and remember no current flows into the gate of this thing, the voltage is changing here, that changes the current going through here, and we get an amplification across this resistor. Okay, so that's nicely biased, and that's how it works. Right, so as an example then, let's use this 2N3819, which has KT of that, and a threshold voltage of minus 3.5 volts, and we want the bias current to be 0.1 of a milliamp, because we know that that gives us a nice gain of 28. What value should RS be? So RS is this value, this new resistor we've introduced here, which is the thing that's going to allow us to adjust this VGS voltage. Which value should it be? So we can try an analytical approach. What is the purpose of CS? Which one's CS? The purpose of CS will become apparent in a minute. Ignore it at the moment. Okay, so we know that in the flat region, this is the equation for ID relating to VGS. We know that ID we're aiming for is 0.1 of a milliamp. We've got value of K, we put that in there, we've got 2, we've got various other values in here. We know VT is 3.5 from the data sheet of the device. And all we've got to do then is put in all our unknowns, and hopefully it will leave us with VGS. And so if you put all the numbers in and follow it through, you get VGS is equal to minus 3.15 volts. So we want a value of VGS across here of minus 3.15 volts. But we know that VG equals 0 because it's tied through this resistor here. So we know that the one end is at 0 and we want 3.15 volts at the other end. And it's easy then to apply Ohm's law to this resistor to get the value of 31.5K in that case. So if we make this resistor 31.5K, we will get a value of ID of 0.1 of a milliamp. And hopefully that will give us a gain of 28. There is a graphical approach. If you've already got this curve, then all you've got to do is plot a line up here, which is this, it's a load line type characteristic of VG minus IDRS, and where basically this straight line crosses the voltage that you, sorry, the current you want. So you just draw a line, draw over here at ID equals 0.1, and just read off the graph here what VT is equal to, and that allows you to calculate it really easily. It's not often that people worry too much about having this curve, but you can get it from the data sheets, and if you've got a ruler and a pencil, you can work it out quite easily. Right. So remember CS, as someone has pointed out to us. We know from previous calculations that RD was 50k because we wanted the voltage across it to be 5 volts, so it's sitting in the middle of the characteristic. If under AC conditions we include CS and we assume that there's a short circuit at signal frequencies, the gain of this system is 28 because it bypasses RS. Okay, if you've got a pen up, if you've got the capacitor across this resistor, and remember this is the AC solution. Yeah, we've done the DC solution now where this was open circuit. Under AC conditions, when there's a signal coming in, an AC signal, yeah, the capacitance looks like a short circuit. And if it looks like a short circuit, then, so here's a capacitor here looking like a short circuit. If it looks like a short circuit, we've actually got a wire, equivalent of a wire, bypassing this source resistor. And so any current in this part of the circuit will want to go through that wire and not through the resistor. It's like an extreme current divider. So we bypassed it because at high frequencies this is a short circuit. I'm going to razor, get rid of that. It just confuses people if it's still there. So at high frequencies it's like the resistor's not there. So we're back to our original circuit. And then we can analyse that through this small signal model, and we know we've got GM-VGS driving a current. This resistor's been bypassed through the capacitor. Current flows through the resistance, and we get back to our original circuit of minus 28. So GM-RD, RD was 50k, gain of 28. So we've managed to get whatever bias conditions we wanted, with including this source resistor at DC, where the capacitor is an open circuit and therefore the resistor is in the circuit. Okay, but at AC, at signal frequencies, the capacitance is short circuited and therefore this resistor is now out of circuit, and it all simplifies back to our original very simple model. So we get a gain of 28 with that capacitor in place. If you didn't have that capacitor in place, okay, then this resistance is no longer bypassed, so it must be included into the circuit. So here's the small signal circuit with that resistor actually in play. Okay, so this is the model of the FET. This is the input side. Remember VG, there was nothing attached to it. It's sort of, you know, so it looks like it's not quite finished because there's this sort of physical gap between the two terminals of the FET. But nevertheless, this is what the model is. We know that under these conditions GM is 0.56 millisiemens. We know 50k, we can put everything back in here. We've got enough now to calculate this, but it's a slightly more complicated because we have to take this resistance into account. So we can say that Vin equals VGS, whatever that voltage is across there. So it is slavishly applying the rules. That's VGS across there, plus GM RS VGS. Okay, VGS is the current going through here. There's no current coming through here, and we multiply that by RS to give us the voltage. So we've just done a voltage loop around here. Okay, added up all the voltages around this little mesh. So you've got GM VGS as the current flowing through here, which is this bit and this bit, and RS turns that into a voltage for us. So we've added up the voltages around this loop, and therefore we can rearrange this to give us VGS equals this, and we know that V out is the voltage across this resistor here, and that's going to be GM VGS, that's the current flowing through here, times RD, which is what we had before. But now VGS is no longer V in, it's this expression here. So we have to drop that in to VGS here, and this gives us this expression here. So now our relationship between V in and V out is a little bit more complicated. And if we can say that GMRS is bigger than 1, so that this is significant compared with this, we can ignore that, because if this is big, say this is 100, then 1 plus 100 is 101, and that's close to 100, so we just call it that. And then obviously we can just cancel out the GMs, and we end up with V out over V in is approximately equal to RD over RS, which is the ratio of these two resistors. And I say as expected because that's exactly what we got with the bipolar transistor with the emitter resistor in place. So if you think back to the bipolar transistor, this kind of arrangement with a resistor in this, well, call it the emitter or the drain side of things, or the source side of things, with a bypass capacitor around it, allows us to stabilize the DC bias conditions, which fixes our gain, but allows us to maintain a high gain at signal frequencies because the capacitor bypasses it. Okay, so it's another introduction of this idea of stabilizing feedback, which is then got rid of at signal frequencies to allow us to have the high uncontrolled gain again. And in this case, RD over RS would give us 1.58 or so. So we get a low gain. So the full small signal equivalent circuit of the model, and I say full. Okay, full always means, and this is helpful for exams, okay, full means include all the components even if they appear to be short circuits or whatever to you. Make sure you put them in so you know they're there. So we've included all the capacitances in this full small signal equivalent circuit. So we've got input capacitance for decoupling. We've got the biasing or the pull down resistor, RG, which we can quite often ignore because it's very, very big. But in a full model we have to put it there so that we can decide whether to ignore it or not. We've got a bypass capacitor, the source resistance, the drain resistance, and the signal source. Yes, I've run into problems with PowerPoint again. These are all little V's. Okay, it automatically capitalizes it and I just want to slip through, but I'm sure you all know that now. Likewise, this it's just made this into a capital because it can. It should be a small g. Right, so that's all good. It applies, so you can see how a lot of the bipolar stuff that we did starts to apply to the FETs as well, which is quite nice. But we have a slightly simpler small signal model because we don't have to worry too much about R-pi because one doesn't exist. Right, so let's revert back to having a look at what's going on in these FETs. Let's think about what's going on. So we've got these two regions. We've got the linear region, sometimes called a triode region, but we'll call it linear, and we've got this saturation region. And we've got this basic curve for output current against the drain source voltage. And we remember that this makes it into a constant current source, this flat bit here, because it doesn't matter what we make VDS in this range here, the current stays the same. In region 1 we have the equation of this with various restrictions that say it has to be in that first rising quadrant and can't go past the first turning circle. That's all this is saying. If you want to sit down and think about it, you're welcome to, but it's just telling us that it only applies in this bit and it doesn't do this. Even though the equation does this, it doesn't apply in our physical model. And it's also saying it's not telling us anything about what's going on down here either. Okay, so how does this equation actually behave in the linear region? Is it really linear? No, so the linear region is the rising bit. Okay, we've got this equation here, which if we expand it out becomes ID is equal to K BDS, which is single power, and then K BDS squared. So we've got a quadratic equation here in VDS. Okay, VDS squared, VDS, and a constant that's 0. So what we're really saying is that everything in this equation is constant if we're in that region, apart from VDS really. So if VDS tends towards 0, which means that we're operating at close to the bottom of that curve, then ID tends towards BGS minus KVDS BGS. So this square term gets smaller much quicker than this term does. Right, yes, there's a graph coming up in a minute which shows it better. So we can say that for very small, at the bottom of the curve, for very small values of VDS, then this quadratic equation is effectively a linear equation, because this is a very small value when VDS is small. If VDS is small, V squared VDS is much smaller. Yeah, that's what happens with small values when you square them; they get very small. Big values, you square them, they get much bigger. That's down here. Okay, so we're saying that this bit of the equation is the equivalent of a linear equation for full small values of VDS. Okay, and your definition of small is up to you, but you can see that as VDS gets bigger, it gets less linear. So this bit is nice and linear, this bit is less linear. But in some worlds you might say, well, that's still quite linear, I can live with that. Just depends. But eventually it starts to become, the square term starts to become significant, and we end up with this turning point, and we start to get we get what it is, a parabola. And so if we followed this all the way through, we would end up with this curve going right back down again. Okay, so this is where the limitation of the equation for region 1 is one of the limits here. It obviously can't go down anymore, it just sits flat. What happens then is that we say we're now in the new region. That's the boundary between the region 1 and region 2, and now at this point the region 2 equation takes over for our model. So we've got a piecewise model. We create a model that says it's curvy and square lawry up to this point, and then the other equation applies from that point on, and they've got to join up at this point. Right, so we figure out the transition point by just differentiating that equation, and that tells us what's going on. So that's straightforward enough, I think. If you understand what differentials are, you get the turning point, and that work tells you what the maximum value is. So in the second region, we've got the other equation, which is this one. And again, there are some validity issues here, but this is really just saying it joins on to the other equation when we get to the turning point. Okay, and this current does not depend on VDS, and we've gone through this many times now. It's a constant value. So using the transition point we calculated by the differential, we can switch between two regions to get a complete curve for ID, which is what I've just said. So we just do the first equation up to this point. We've calculated the turning point, we know where that is, and then the other equation just so happens that it's the same value as the turning point, and that goes in flat, and that's how we generate our model. Okay, so that's all good, and we bear that in mind because that's going to be important going forward. So we've done our common source amplifier, and now we can start thinking about this high impedance unity gain buffer, which is a neat little trick actually. So this is the amplifier that we, well, basically without this resistor here, it's called a source follower. So it's a bit like the common collector stage that we had for the bipolar stages. So if we look at this common collector equivalent circuit for a FET, which is called a source follower, remember for the bipolar transistor we didn't get any gain in terms of voltage. We just got V out to be the same as V in, except 0.7 of a volt smaller, but we got big current gain, and we decided this was probably a good thing at some point. This is the same kind of configuration. We're starting to get the idea what's going on, but we can see that V out is probably just going to follow V in this configuration because there's no multiplying resistor up here. and whatever VGS is going to be the difference between V in and V out. What we would really like in a buffer, an ideal buffer, because remember a buffer is just something that isolates one part of the circuitry from the other part of the circuitry. We would like the difference it to be 0, so we have V out is equal to V in. So if we put a certain voltage, say 1 volt, into our buffer, let's go back, put 1 volt in here, in an ideal buffer the output would also be 1 volt. So if we've got a 1 volt signal going up and down here, ideally we'd like the same 1 volt signal coming out of here, and it'd like it to be identical. The only difference is, of course, is that it's been isolated by this device in the way. Otherwise we could just use a piece of wire. So there's obviously something else going on, and it's to do with impedances. So this allows us to exactly replicate this voltage here, a buffer. So a buffer will allow us to replicate this voltage here, but it allows us to magnify the current that it can drive. So we've turned it into a low impedance source from this side. So that's what we want to do with the buffer. We want to make sure that whatever we get coming out of here is the same as what's going on here. Now the bipolar one got close. It was the same coming out as went in, but just dropped by 0.7 of a volt, so there's a little offset. Be nice to see if we can actually get a 0 difference. So what we want is for V out to equal V in without any offset, and we can achieve this if VSS over RS equals IDSS, because then VGS equals 0. You can probably see it easier from this. If VGS, which is the voltage across here, is 0, which we know we can get when ID equals IDSS, yeah, then V out must equal V in, and it's as simple as that. So that's what we're looking for. We're looking for V out is equal to V in. This is not a join. Okay, there's a little jump across there. Okay, so that's not a join. That's just the signal's been folded over on itself. Right. So small signal analysis of that circuit, the buffer circuit, if we can say that V in is equal to VGS plus GM-RS VGS, because we've got this current flowing through here, and we want the voltage to do the voltage around this loopy thing here. So we've got GM VGS RS plus VGS equals V in, and we know also that V out, remember this is not a join, this signal comes out and that one isn't, it's just going to be whatever the current is flowing through here multiplied by RS, because that's where we take our output voltage from. Okay, and then if we make the substitution then for VGS to get us a V out over V in, so we've seen this many times now, we get GM RS over 1 plus GM RS. So the relationship between V out and V in is equal to 1, okay, which means V out equals V in, if GM RS is large, and we can ignore this here. Same kind of things. Okay, so that's what we're heading for. So one way of making RS large and guaranteeing that equation is to use a current source, because the impedance of a current source is infinite, because it's constant, doesn't change its current with any kind of change in voltage. And one way of making a current source is to use a transistor or a FET that's suitably biased. So this is where it starts to get quite interesting. So we've got two transistors in this circuit. Let's consider this circuit. So we've got our input to our FET transistor, we've got our output here, and we've replaced the source resistance with this transistor, right? And this transistor has been configured so that its gate has been tied to its source. Yeah, and if we tie the gate to the source of any device here, then this thing biases itself so that IDSS flows through this device. That's the law of the FET. Alright, so we've got VGS here, we've got its VGS is naught, obviously, because both VG and VS are tied to the same voltage, so the difference between them is 0. Therefore, this transistor is doing its utmost to make IDSS flow through here. And the only place that can come from is this transistor. And they're identical transistors in an ideal world, and therefore this transistor is being told by this one, effectively, give me IDSS, I'm pulling IDSS through me, it's got to come through you. And this transistor is saying, okay, well if it's coming through me, then I need to make sure that my VGS is the right value. So it's sort of in reverse. It's saying the current going through here is IDSS, therefore the voltage across here must be the equivalent value of VGS, which is 0. So this one says my VGS is 0, I'm pulling IDSS through myself. This one says, oh, the only way you can get that is if I make my VGS equal to 0. And then it's quite happy, because then we've got 10 milliamps thrown through here, 10 milliamps thrown through here. Both VGS's, bias condition VGS's, are the same. And as this one happens to be 0, this one's 0, and therefore Vout is equal to Vin, because Vout is only different from Vin by VGS, which we've got across here. So Vout equals Vin. And that's because this is a perfect current source in this region here. Say perfect, close to perfect in that region. So if we can make this resistance or equivalent resistance here to be a current source, the value of the resistance of that is 1 over the slope of this, which is infinite. So we've made a huge resistor, but only for AC. Okay, so in words, if T1 and T2 are identical and both are in region 2, then T2 forces the current ID to be IDSS with a grounded gate, and therefore VGS for T2 is therefore 0 as well. As T1 is the same as T2, they're both the same identical transistors, then both VGS's must be the same and 0. Therefore Vout equals to Vin minus VGS equals Vout, it equals Vin. So that is an incredibly useful circuit. Two transistors identical. There's no resistances in this. This is the beauty of transistors. They can do all kinds of clever things. So this makes the perfect buffer with a couple of transistors. Why is VGS 0? Because VGS is the difference between VG and VS. Yeah, that's the definition. VGS is VGS is the definition of the value of VG with respect to S. And both of them are at the same potential. So the difference between them is 0. Okay? Yeah, in T1. That's the point. If the current through here is 10 milliamps, which it is, IDSS, because VGS is equal to 0, then the current through here must also be the same, 10 milliamps, because it can't come from anywhere else. Nothing connected here, no current comes in through here. The only place current can come to make this one 10 milliamps is up here. Okay, and if that happens, this transistor must have a VGS of 0. That's the clever bit. Otherwise, current can't flow. If VGS is not 0, current can't flow. It's being pulled through by this bottom one, and this one's saying, okay, well I'll just adjust myself accordingly, and that's just it's just how the equations work out. That's what happens, and it's brilliant, elegant, and wonderful. Yeah, it is. I think it's really good. I think it's really neat, and it's so simple, and it works really a lot. And that circuit is used almost everywhere, but it's particularly used in oscilloscopes to allow a high input impedance on your oscilloscope. So when you attach an oscilloscope to a circuit, it doesn't take any current, and so you don't affect the signal that you're measuring. So it's very important to have high input impedances on measuring equipment, so that you don't affect the thing you're trying to measure. Okay, right. So at that point, it's probably a good point to stop, and you need to go back and reflect upon that, and make sure you understand the elegance and beauty of that particular configuration and circuit, and then we can use that idea and other ideas going forward to actually do some really clever stuff with analog signal switches and other amplifiers going forward. So I've just been cut off. That's a good point to stop anyway. I'll just wait till it reconnects. So we're still waiting to connect. Still reconnecting. Right, okay, so it's not going to let me reconnect, so I shall stop.